Our next speaker will be Hoi Yip from the University of British Columbia, who'll be telling us about maximal cliques of Cayley graphs over fields. So I'll hand it off to our speaker.
Okay, thank you very much for the introduction. So in this talk, I will talk about maximal cliques of Cayley graphs over fields. So let's begin by recalling the definition of Cayley graphs, maximal cliques, and also maximal cliques. So for abelian group G and the connection set S, such as S is a symmetric set, we can define a Cayley graph on the group G with the connection set. So it's denoted Cayley GS. So this is a graph whose vertices are element of G, and the two vertices are adjacent if and only if their difference is inside the connection set S. So this is the definition of a Cayley graph. And a clique of a graph is just a subgraph that is a complete graph. A maximum clique is a clique with the maximum size. And for a graph, the clique number of x denoted omega x is the size of a maximum clique of x. And a maximal clique is a clique which we cannot extend it. So this is the basic terminology. And the motivating question for this talk is the following. So given a Cayley graph, is there a way to construct a clique C explicitly, such as this clique C is a maximal clique, but it's not maximum. So we want an explicit construction of such clique, which is a maximal clique, but not maximum. The question was first asked by Goyanov, Kapnov, Salaginov, and Varaginich for Cayley graphs with square order. Cayley graphs are basically a special case of Cayley graphs, and we will define that shortly. In general, it's challenging to construct such examples explicitly if X has a large order. And the simple reason is that finding the clique number of a graph is amply complete. So that means there is no efficient polynomial time algorithm to find the clique number of a given graph. So that means if we are given a maximal clique, in general, there is no way to see whether it's maximum because we don't know the clique number. So we don't know whether a maximal clique is maximum. So that means we need to restrict ourselves to certain special Cayley graphs. And before doing that, we need to recall one more result, which is proved by Green and Morris. So they use probabilistic method and also tools from additive combinatorics and also regularity lemma to show that the clique number of almost all Cayley graphs defined on cyclic group G is of the order log of the size of G. If all cliques have logarithm scale, then it's unlikely we can construct any maximal clique explicitly because the clique number is so small that we don't see anything special about any maximal clique. So based on these two observations, we will focus on Cayley graphs with clique numbers significantly larger than the logarithm scale. In that case, we expect the graph has some additional properties, which gives us some hope to construct maximal cliques explicitly. And then we will try to check whether these maximal cliques are indeed maximum or not. Okay, so the following is our main result. It's basically gives a new family of maximal cliques of Cayley graphs over fields. And the setting is a little complicated, but I guess it's okay. So we consider field F, and we denote F paths to be its additive group. And we also need to choose the connection set S. So S is a subset of F minus the 0. And we want -1 to be S so that S is symmetric. And we also want S to be closed under multiplication. Then the Cayley graph we consider is the Cayley graph defined on the additive group F paths with the connection set S. If we assume that K is a proper subfield of F, such that the degree of extension of F over K is finite, and K forms a clique, then we can conclude something about maximal clique. So basically, we can find a subspace V of F over K, such that K is containing V and V forms a maximal clique index. So roughly speaking, we can find a maximal clique with a vector space structure under certain assumption. If we also assume the axiom of choice, then we can drop this condition on the finiteness of the degree of extension. So because here we need to use something like every vector space has a basis. So if the dimension of the vector space is infinite, we have to assume the axiom of choice. So this is our main result, and we will try to apply it to certain Cayley graphs. We'll apply it to study the maximal cliques of certain Cayley graphs, satisfying these properties. So as I mentioned earlier, we should define Cayley graphs and also generalized Cayley graphs because they form a class of nice and well-studied Cayley graphs. So Cayley graphs are defined on the additive group FQ parts of a finite field FQ, where we need to assume that Q is congruent to 1 module 4 because we want the graph to be an undirected graph so that we can talk about the clique number. So the Cayley graph on FQ, denoted PQ, is the graph whose vertices are elements of FQ, such as two elements adjacent if only if their difference is a square in FQ star. So in other words, PQ is just a Cayley graph defined on the additive group FQ paths with the connection set being the squares in FQ star. So we can imagine that Cayley graphs are just two Cayley graphs because the connection set are squares. So we can define D Cayley graphs, and they were first introduced by Cohen in 80s. Similarly, we also need to assume that Q is congruent to 1 module 2D to make sure that these graphs are undirected. Then we can similarly define the D Cayley graph on FQ. So it's denoted GPQD. G stands for generalized and the P stands for Cayley. So this is the D Cayley graph on FQ, GPQD. So it's a special Cayley graph. So it's a Cayley graph defined on FQ paths with the connection set being the dispowers of FQ star. This is called D Cayley graph. And we will try to apply our main result to study the maximal cliques of generalized Cayley graphs. Before that, we should revisit our the motivating question. So, but before that, we need to talk about the chief upper bound on the clique number. So, if we are given a generalized Cayley graph with order Q, then the chief upper bound is given by root Q. So this is called the chief upper bound because to prove this, we just need like 2 line proof to prove that. And for the lower bound on the clique number, it's often helpful to consider whether a particular subfield forms a clique. So in particular, if Q is a square, and if we can check that F root Q actually forms a clique, then this chief upper bound is tight. And for a Cayley graph with square order, it's with families of maximal cliques that are not maximum unknown. So this is the motivating question. So this is a result proved by Goryanov and 3 other authors a few years ago. So they consider the Cayley graph is order Q square. So in this case, it's easy to check that the clique number is given by Q. And they were able to explicitly construct maximal clique of size half Q plus 1 or half Q plus 3 according to the congruence condition. So we can see that because the clique number is Q and they found some maximal clique of size roughly half Q, that means they found explicit construction of maximal cliques which are not maximum. So this is something very interesting. And we would like to explore something similar for generalized Cayley graphs because this is just for the standard Cayley graph. So to do so, we need to revisit our main result and try to see whether it can be applied. So, so this is our main result. And for our purpose, we will take the field F to be a finite field, FQ. And if we take F to be a finite field, then because S is a subset of FQ star and S is closed under multiplication, we must have S to be closed under inverse. So based on these two conditions, we can immediately conclude that S must be a multiplicative subgroup of FQ star. Now, if we go back to the definition of generalized Cayley graphs, they are Cayley graphs defined over a finite field FQ with the connection set being like these powers of FQ star. In particular, the connection set is a non-trivial multiplicative subgroup of FQ star. So therefore, in the case that the field F is a finite field, we can see that the Cayley graph X defining our main result is exactly given by a generalized Cayley graph. Therefore, our main result can be directly applied to maximum cliques of generalized Cayley graph. So we immediately get the following corollary. In this corollary, we consider the generalized Cayley graph GPQD, where Q is P to the dr and D divides Q minus 1 over P to the r minus 1. Then our conclusion is that either Fp to the r is a maximal clique, or the clique number of GPQD is at least Q to the 2 over D. And here the condition D divides Q minus 1 over P to the R minus 1 simply guarantees that Fp to the R forms a clique in GPQD. So we can apply our theorem to say that we can find a maximal clique which has a vector space structure. So it's a vector space over the space field Fp to the R. Then we just have two different cases. The first case is that Fp to the R just forms a maximal clique. And the second case is that it's not a maximal clique, so we can find a vector space of dimensional at least 2 over the space field Fp to the R. So that means the clique number of GPQD is at least Q to the 2 over D, because it's the size of P to the R square. Based on this corollary, we can come up with the following conjecture, which basically says that we always have the same, we always have the first case. So Fp to the R is always a maximal clique. So we don't know whether the clique number is larger or smaller, but we conjecture that Fp to the R must be a maximal clique because this clique is so special, it's a subfield. So for Cayley graphs with square order, we have seen that this statement is trivial because of the trivial upper bound. And in the next few slides, we will show that this conjecture is true for cubic Cayley graphs with cubic order and quadruple Cayley graphs with quadratic order. So I forgot to define what's cubic Cayley graphs and quadruple Cayley graphs, but you can guess that they are just 3 Cayley graphs and 4 Cayley graphs. But this conjecture is widely open where D is at least 5. So let's just see a quick proof of the maximal clique result for cubic Cayley graph with cubic order. So that Q to be P3R, then we can conclude that Fp3R, the subfield with P3R element, forms a maximal clique in the cubic Cayley graph with order Q. So basically, we can prove by contradiction. So suppose it is not the case, then by the previous corollary, the clique number will be at least P32R, which is Q to the 2/3. So recall that the triple upper bound for the clique number is given by root Q. So that means this is not possible. So that means Fp2R must be a maximal clique in the cubic Cayley graph of order Q. And based on this theorem, we can try to partially answer the motivating question for cubic Cayley graphs. So we can consider a special class of cubic Cayley graph. So we assume that P3R is congruent to 5 modulo 6. In this case, we can use this theorem to conclude that F_P2E2R forms a maximal kick in the cubic Paley graph with order P2E6R, while the kick number of this graph is given by P2E3R because one can easily show that the subfield with P2E3R elements also forms a kick. So that means for this class of cubic Paley graph, we have explicitly constructed a maximal kick in a cubic Paley graph, which is not maximal. And I will quickly finish the rest slides. So for quadruple Paley graph with quantity order, we also have a similar result. So if Q is P2E4R, we can also show that F_P2E_R is a maximal kick in the quadruple Paley graph with order Q. And similar to the cubic Paley graph case, it suffices to show that the triple upper bound Q on the kick number is not tight. So in general, it's very difficult to improve the triple upper bound on the kick number. In particular, if Q is a square, improving the upper bound by 1 already requires a lot of work. So this is my result, and I basically spent about 12 pages to prove this result. And the proof is number theoretical, so it's based on Carter sum estimate and Gauss sum, and also classification of maximal kicks. It basically says that the kick number of GPQD is given by root Q if and only if D divides root Q plus 1. In particular, in our setting, in our quadruple Paley graph setting, Q is P2E4R and D is equal to 4. So we can check that 4 does not divide P2E2R plus 1. So that means that the kick number is at most root Q minus 1. So that means the triple upper bound is not tight. So that means we can prove the claim about the maximum kick of the quadruple Paley graph. And that concludes my talk. Thank you very much for your attention.
Okay, thank you. Everyone, let's thank our speaker. Feel free to clap react on Zoom. And it looks like we do have a couple of minutes for questions, if anybody has some questions. I did have a question. I was wondering if you could comment more on the algebraic meaning of something being a maximal clique. Is it always a subfield in the case where we're doing the Cayley graph of a field?
No. So, I mean, there are many different maximal kicks. So if we start from a random vertex and then try to randomly expand that, then we will get a maximal kick, but it's like it don't have any special structure. But if we want to explicitly construct such maximal kick, then the only thing known is that it has a vector space structure. But we cannot say that every maximal kick must have a vector space structure.
Can I ask one question? Sure. So I see that in this result, is the role the number theory plays is that it gives a nice family of combinatorial examples in terms of Cayley graphs. So reversely speaking, do you think that this Cayley graph also says something number theoretic about these finite fields?
Yeah. So in our case, we just apply this theorem for generalized Paley graph. And if you look at the definition of generalized Paley graphs, yeah, so this is the definition for generalized Paley graphs. So you can see that this graph is actually characterizing certain arithmetic structure of the finite fields, the element in the finite field. So, for example, for the standard Paley graph, it means that the difference between every two elements is a square. So this is a very special the set. So it's connected to many problems in number theory. For example, the cattle sum estimate, for example, Riemann hypothesis, the least quadratic residue. So they are all connected. And we phrase this as in the language of graph theory because it's easier to understand that.
Okay, everybody, let's thank our speaker again for a great talk.
Thank you very much.